Hi everyone. I've been thinking about something that actually was the problem that actually got me interested in mathematics and physics way back when. So in high school, I was very much interested in math, but one area of mathematics just set me on the course, and that was this question of prime numbers. So there's a lecture actually I watched. I can show you guys. For those of you that are interested. Let me see if I can find it. So it's from Professor Jeff Waller at the, I think it was University of Texas. Um, but my internet's really slow, sorry. Just give me a second. So, and it was a lecture actually on the Riemann hypothesis. So let's see if I can load it. Yeah, so it was this lecture. So it was done in 2001. So that's when I was in the 11th grade. 2001, I was in grade 11. And I was in a library and I watched that lecture and I was immediately hooked into mathematics. Because this whole issue of the distribution of prime numbers is one of the most kind of interesting questions that I've ever kind of seen. It's very profound. So I have a Mathematica notebook open here, and I will show you what I mean. So let me actually just save it out of paranoia. So let me just save it. Let's call it primes. Right. So it's kind of, so what I mean literally is what I mean by distribution of prime numbers. So if I kind of, list the first, let's say 100 prime numbers. Right. So you can see like these are the first 100 prime numbers. So like 2, 3, 5, 7, 11, 13, 17, all the way to 541. I can list the first 1,000 prime numbers. So this is why I'm using Mathematica. It's really fun. So you can see it's pretty interesting. And the question really is that, aside from just the interest of prime numbers in general, but the question really is there any deep pattern between how these prime numbers are distributed? And that's really the question that is at really one of the strongest implications of the Riemann hypothesis, but all the great work that Riemann did. So as an example, like if I wanted to know how many prime numbers there are less than, let's say, 100, well, you can count here, right? So this is 101. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So there's exactly 25 prime numbers that are less than 100. And likewise, if I want to know the amount of prime numbers less than 1,000, then you would count, how many prime numbers there are less than 1,000. So it turns out that this list is about 168. Actually, it's exactly 168. And for 10,000, it's about, it's exactly 1,229 prime numbers and so forth. And I think by now they have computed up to like 10 to the 27. So they know, based on rigorous computations, how many prime numbers there are less than a certain number. So you can imagine that, okay, for small amounts, like small values of n, this is easy enough to count. Like, for example, if you wanted to know the number of prime numbers that 10, you can just count this list, right? And for 110,000 and so forth. But actually, one of the kind of most profound theorems in mathematics is this notion of the prime number theorem, right? So let me actually write that out. And so if I denote, let's say, by pi of x, and denote that as a function called the prime counting function. So, denote by, let's say, pi of x to be the prime counting function, and this will denote the number of primes less than x. And so what this is very fundamental is that the genius of, and one of those profound ideas in mathematics really came from Riemann. And so Riemann, and there's a lot of history behind it, and I'm just kind of on my break right now from my work, so I thought I'd make this kind of quick video, numerical experiments, but there's obviously wealth of information behind this. And what Riemann did was he came up with an exact formula for pi of x. And that is just downright crazy, that somebody can have an exact equation that tells you what the number of prime numbers less than the number of x. So you can get the exact number, and it's absolutely crazy that you can do this. And it's something very deep and profound, that there's a function that actually can count the number of prime numbers, and more so, it's an analytic function, and more so, it was derived by Riemann, and it's one of the most profound formulas. So I can actually just type it out here. I probably have to type it in LaTeX, because I don't know yet how to actually put LaTeX directly into Mathematica, but it's easy to type. So like pi of x is equal to r of x, and I'll explain what r of x is in a second, minus sum, let's say, over the row, and I'll explain what these are in half a second, but just bear with me. Minus 1 over log of x plus 1 over pi times the arctan of pi over log x. And I should probably be a bit more LaTeX-y. Sometimes I get confused when I'm in Mathematica versus LaTeX, but it's the same idea. Okay, there we go. So, I mean, that's the formula. So, the genius, as I said, of Riemann is that he came up with an exact equation that tells you how many prime numbers there are less than a value x. So the idea is that if you put in an x, let's say 1,000 or 100, you get the exact number of prime numbers that are less than that value. So as an example, like, first of all, what are these functions? So this function, it's typically called the Riemann R function. So as an example, this R function is called the Riemann R function. It's probably called something else more formally, but in school and stuff, I always heard it as the Riemann R function. And so that's defined as the following. So let's say summation from n equals 1, it's an infinite sum, and then mu of n, actually I'll make it this nicer frag, but mu of n over n times li of x to the 1 over n. And so li is the logarithmic integral function. So for those of you that do not remember from your special functions course, but I don't know why LaTeX is taking a long time. It's probably just the video that's causing the delay in processing. That's fine. So that's the Riemann R function. And this function mu of n is a very peculiar function, actually. So this function mu of n is known as the Mobius function, and it's in itself it's a very peculiar function, but it's actually pretty pretty important in number theory. So the way it works is mu of, let's say, n is equal to 1 if n is a number with an even number of prime numbers, of prime factors, sorry. It's equal to -1 if it has an odd number of prime factors, and it's equal to 0 if it has a squared prime factor. So a Wikipedia article on the Mobius function has a lot more details about this, but just roughly. So for example, like 1, so the Mobius function of 1 will be equal to 1, but the Mobius function of, let's say, 6 will also be equal to 1. But let's say that the Mobius function of 9 will be equal to 0, because 9's prime factors are 3 and 3, so 3 squared. If you actually look at what's the example of -1, so odd number of prime factors. So for example, 2 would be, Mobius function of 2 would be equal to -1, because it just has the single prime factor, so it's just one prime number, so it's an odd number, so it's -1, and so forth. So that's the Mobius function. And so the only other thing to explain then is this whole business of the Li function, and this is the logarithmic integral function. So these are you start to get into the domain of special functions in the area of when you go deep into number theories, because these integrals and these distributions are very complicated, so you need non-standard special functions, and the logarithmic integral function is one of them. So just as a definition, I'll just put it here. So it's typically defined as an integral, so it's an integral function, and let's say frac of 1 over log t dt. I think my screen being recorded on my little MacBook Pro Air here is causing delays in computational things, but whatever, it's fine. So that's the logarithmic integral function. So what the Riemann R function does, it's just an infinite sum, basically, of the Mobius function times the logarithmic function, but with these as its arguments. So like x to the power 1 over n, and this is just mu n over n. And so that's the Riemann R function. And so if you go back here, that's the first term in the prime counting function. And then what Riemann's kind of true genius was, this was known as an approximation right up to this point. So if the pi of x is approximately equal to this r of x function, so it was proportional to the logarithmic integral function. And historically, people already knew that. Like, I think going back to, and I'm going to put my foot in my mouth when I say this, but I think going back to Gauss, but it could not be Gauss, maybe it was, I think it was by Gauss actually, 18th century, that it was the number of prime numbers is related to the logarithmic integral function. But nevertheless, so that was Riemann's genius, and what Riemann figured out was that there's these extra terms here that if you add them, you get a precise equality. And so I can't stress that enough. Like, there's an exact analytical equation, a formula, that actually tells you exactly, not approximately, not some, relying on some just approximations. It's an exact equation that tells you that if you enter in the boundary that you're seeking, like 1,000 or 100 or 50, this pi of x equation will give you the exact number of prime numbers that are less than that number. And so, so this is pretty self-explanatory. Like, r of x I just defined below as the Riemann R function. 1 over log x is just, standard kind of log function. The arctan function is pretty standard as well, so nothing kind of really complicated here. The interesting thing is here in this second term here. So, this is a very kind of deep result here. And so I'll explain that here. So, just out of laziness. So the interesting thing here is the second term in the equation, which is a summation over this kind of variable rho applied to the Riemann R function. And so that's really the whole kind of charm and the whole kind of depth of this equation is in the second term. And what these rho are is exactly, so rho here represents the non-trivial zeros of the Riemann Zeta function. So it's pretty crazy, right? And this is why the Riemann hypothesis is such a deep thing, because while there's a lot of reasons why, but one of the most profound applications in proving the Riemann hypothesis, and in particular where those zeros are along that critical strip in the complex plane, that will tell you something very deeply about this summation here. And so what that basically is saying is that if you know where all the zeros are, or the non-critical zeros, because this equation works with the non-critical zeros of the Riemann Zeta function, you can then write down this equality. So this equality depends entirely on knowing where the non-zero or non-critical zeros are of the Zeta function. So for those of you that don't remember, I can remind you what the Riemann Zeta function was. So it's really just, it's not very complicated in its kind of original form. So the Riemann Zeta function, this is Zeta function of S, so I can kind of define it as, it's just defined as a series. So Zeta of S is equal to sum of to infinity and frac of 1 to the n of S. Okay, it's done. Okay, and so it's not very intimidating when you write it down like that, but actually it's pretty complicated what the implications are of the Zeta function. So as an example, so what I should mention to start with really is, the first thing is that here S is not a real variable, but it's a complex variable. So typically you write something like S is equal to sigma plus IT. So T is the parameter that you use to parameterize the complex argument here, but it's a complex variable. So this is not a function of a real variable, it's a function of a complex variable. And the most important thing is this converges. So this series, you can prove it converges for S being greater than 1. So that's really the thing of the Riemann Zeta function. So what's really deep about this is that, as with any function, you have zeros, right? So you have zeros that are associated with this. So ideally, what values of S, for what values of S does zeta of S equal to 0. And so this is the main difference here, is that you can break this up into what are known as the trivial zeros and the non-trivial zeros. So one of the easiest ways to kind of see this is actually from the functional equation. There's a way you can rewrite this Riemann Zeta function, and I don't remember what it is off the top of my head, but there's a way to do it here. So there's a functional equation that was derived by Riemann as well, that is equivalent to this series, and so I can write it out. So zeta of s is equal to, so it goes like 2 to the power of s times pi to the power of s minus 1 times, let's say, sine, make my fracs, so pi s over 2, yep. And then in terms of the gamma function, so gamma of s minus, or 1 minus s, gamma of, and it's actually zeta, once again, of 1 minus s. Okay, and I'm going to get into trouble with that. Okay. So that's another way, this equation is another way in which you can talk about the Riemann Zeta function. So you can see that there's two occasions in which this function has zeros, right? So right now the sine function here, it's very easy for sine of x to go to 0. It's just when you have n times pi, right, basically. So if you have pi of s over 2 is equal to n pi, this will give you basically all the negative integers. So these are referred to as the trivial zeros. So the trivial zeros are where sine of pi times s over 2 is equal to 0. And that's very easy to see. There's a bunch of non-trivial zeros, right? So there's also a number of zeros, in fact an infinite number of zeros. Riemann actually proved that there's an infinite number of zeros that do not correspond to the trivial zeros here. So that's really the thing here. So the non-trivial zeros are much more difficult to find, but Riemann proved that there are an infinite number of them, and more so, all of the non-trivial zeros have a real part equal to 1/2. So all of the non-trivial zeros, they actually lie in the complex plane, but they lie actually on an exact line. So 1/2 plus it. And so I can show you that. So these are very difficult to compute. You typically have to compute them numerically. So Mathematica actually has a function called zeta 0, and I believe if I will have to apply numerical argument here. So for example, if I wanted to print out the first, let's say, 10 non-trivial zeros of the Riemann Zeta function, I can do it like this. So table of n zeta 0, let's say of x, and x goes to, let's say, 1 to 10. So these are the first 10 non-trivial zeros of the Riemann Zeta function, and you can start to see that each one of them have real part 1/2. So 1/2, 1/2, 1/2, but yet there's an infinite number of them that are actually going. So I can actually plot this, and you can see. So you can see this is the complex plane, And so you can see all of the non-trivial zeros, they lie along this complex complex line actually, which is 1/2 plus IT. So 43, 48, 49, so forth. You can print the first 100. So it takes a second or so to compute. But and so those are the first 100 non-trivial zeros. But you can see remarkably, each one of them lie have exactly real part equal to 1/2. So the idea is that if you go back to this formula, if you sum this Riemann R function over all of the non-trivial zeros, which are these and an infinite number of them, you come to an exact equation for the number of prime numbers. This is really my purpose of my kind of numerical experiment, was to really demonstrate this connection. And so do a numerical experiment that investigates. So let's do a numerical experiment that investigates the Riemann prime counting function. Okay, so so the easiest way to kind of do that really is to come up with a function that I will make one. So it's pretty easy to do this. So the first thing I need to do is I need to have a function that returns all of the non-critical or the non-trivial zeros of the Riemann zeta function. So there's a bit of an issue in the equation, because if you just apply it with these zeros, you'll run into a problem because you actually need the complex conjugates as well, which zeta 0 does not provide. So we'll just build a function here really quickly that actually gives you both the non-trivial zeros and their complex conjugate as well. So I can do that, so it's pretty easy to do. So I'll just flatten the result after. So what I'll do is I'll append to my table of zeta 0, and I'm leaving n as an argument to the function, so I can just specify it after. So zeta 0 of I. Not done. Append table n of zeta 0 of, let's say, I, and I will go from 1 to n. And so what I'll do is I'll append to this function the conjugates, the complex conjugates of these zeros as well. So zeta 0 of I, and then this will go from 1 to n. Okay. So if I try it out just to see, like, give me the first 10 zeros of the zeta function and their complex conjugates, you can see like 0 plus 5 plus, and then has the -1 there. So I will then build my prime counting function to be basically summing over all of these zeros, and then you'll find that actually everything is very, very well done. So Mathematica actually has the Riemann R function built in, which is defined in terms of that Mobius function. So I actually don't have to worry about programming it. But so let's just define the pi function. So I'll call it as Riemann R of x minus the sum of, so this is the sum of the non-trivial zeros. So x to the, let's say, rho, and then my rho will range from, let's say, 1 to the, so let's say I want to deal with the first 10 non-trivial zeros. So really this is a sum over all of the infinite number of non-trivial zeros, but obviously my computer will explode if I go too high with this. So I'm just going to stick with 10 for now, which should be okay. -1 over log x. and then plus that kind of correction term at the end. So arc10 of pi log x. Okay. Alright, so what I'm going to do now is just test out my pi function against a variety of kind of values, so boundaries, so I can, as a comparison to the actual number of primes. So let's say table pi function of, let's say, x, but let's just make x go over precise numbers. So let's say 10 powers of 10, 10 squared, 10 cubed. There's probably an easier way to do this in Mathematica, but just quick and dirty. So all the way to a million, 10 to the 7, 10 to the 8, 10 to the 9, so 10 billion, let's just say. And I should ask for the real version of these. And let's see how accurate it is with respect to the actual number. So you can compute that the actual number of primes very easily in Mathematica by just using, instead of our own pi function, it's prime pi. It should be done quick. It's just eight elements. So you can start to see immediately, like, except for the 10 case, it's pretty accurate. Like, you can actually plot the difference and see. So I can do that. Do the list line plot. This basically takes the percent difference between Riemann's prime counting function and the actual number of primes. You can see that it's almost, except for the first case where I had that 10 case where I had -2, I think, for that, and yeah, -2, and the actual was 4. The rest is actually dead on. Like, as you increase, there's almost perfect agreement between the number of primes and Riemann's prime counting function. And even when you go in smaller kind of boundaries, it's like less than 1% or 2% difference. So it's very, very accurate. And you can imagine, so the accuracy fully depends on playing around with the number of non-trivial zeros you actually include here. And so it's, I put this code in Mathematica. I can link it in the YouTube video. So for those of you that want to play around with this, but that's basically it. So I was just fascinated that you know, this video actually was more of a tribute to Riemann's genius, because the idea that you can come up with an exact equation that counts the number of primes, I think that's just remarkable. So yeah, that's my kind of video and commentary. Let me know what you think in the comments, and I'm happy to answer any questions that any of you guys may have. Alright, until next time, thank you.